done some hard work in this chapter studying splitting fields, and we're just about done. What I want to do is end with a few examples of splitting fields. And if you remember, the key theorem, right, this was theorem 2.1, right? When you want to identify, or if you want to construct a splitting field, here's the standard way to do it, right? If we have some polynomial, and we have this extension, and we have alpha 1 up through alpha n in L are the roots, then the splitting field can be obtained by just adjoining all the roots to the field of coefficients. Right? So we're going to see how that works, or we'll see it in just a second here. So let's look at some examples now. So the first one, so let's just look at the function polynomial f of x equals x squared minus 3 living in q bracket x. Definitely irreducible over q, but of course the roots are plus or minus root 3, and so our theorem tells us if we want to, and by the way, here we're thinking of it, I mean, we have our extension r over q, the roots live in r, and so our theorem says adjoin the roots and you've got the splitting field. And of course we don't need to adjoin both plus or minus 3, it's closed under additive inverses. So the splitting field and this is for x squared minus 3 over q, it's going to be q adjoin root 3. Next example, let's look at x squared minus 2x minus 2, right? Once again, viewing this as a polynomial in q bracket x. If you use the quadratic formula, so the roots are 1 plus or minus square root of 3. Right, once again, living in R. And so, by adjoining both 1 plus square root of 3 and 1 minus square root of 3, we get the we get the splitting field. Of course, adding 1 to it, that's not going to, we don't need that. We don't need both of them. And so, let me say it like this. So the splitting field, if you want to do it without thinking, it's fine. The splitting field, q adjoin 1 plus square root of 3, comma 1 minus square root of 3. It's true. This is the splitting field. But often we do want to be efficient about who we adjoin, because we may want to, in particular, we might want to write down a basis. And so it's easy to see that this is exactly the same as q adjoin square root of 3. We don't need to throw 1 in there because 1 is already in q, and we don't need both plus and minus root 3, just as in the previous example. Another example, let's look at the polynomial x cubed plus 1. Now, this factors, it's equal to x plus 1, x squared minus x plus 1. X squared minus x plus 1. So here's a factorization, right, over q, which tells us then that this polynomial is not irreducible. And so then what we want to do is look at this portion right here, right? Because we obviously don't need to adjoin minus 1 to q, right? So what we're worried about are the roots here. So, and in fact, let me factor this entirely. So this factors as x plus 1, and then x minus 1 plus I root 3 over 2, 1 plus I root 3, is it all over 2? Yep, all over 2, times x minus 1 minus I root 3 over 2. And so if you want a splitting field we've got these complex numbers here. Adjoin these two right here. Of course, you don't need to divide by 1/2. You don't need to add the 1 either. And so splitting field would be Q, so let me write it out sort of inefficiently first. Q adjoin 1 plus I root 3 over 2. Of course, you could even put the -1 there, but that's obviously redundant. And then hopefully it's clear that all we really need to adjoin is the I root 3 part. Okay, so here are some examples of polynomials where we view them as rational polynomials. Let's try a different field now. And this is one, so if you remember, I think it was either last time, I think it was last lecture, where I said we really have two ways to get at the splitting field. One, if you happen to have an extension where all the roots live in that big field right there, then you join the roots to K, and that gives you the splitting field. That's what we've done in these previous 3 examples. But then I also said there's a second one, which is to find it by Kronecker. And so let's do an example of that now. Yeah, I just got blinded. Now I can't see what my example is. Okay, so f equals x squared plus 1, but I want to view this in Z3 bracket x. It's a degree 2 polynomial, and so you can just check, right, that no element of Z3 is a root of this polynomial, which means that it's irreducible over Z3. So now, let's see, what does Kronecker do? Or what does Kronecker say? It says, all right, there exists, if you take an irreducible polynomial, there exists an extension of Z3 that contains a root of x squared plus 1. And so how does that go? Well, you just look at it, let's call it capital F. That's going to equal Z3 bracket x mod x squared plus 1. Now, what does this look like? So let me write this out. It turns out that this is a field of order 9. All right, so it's got 9 elements in there. And let me write them down. Well, what I'm going to do, I'm going to write down the coset representatives, right? So 0, 1, 2, and then it's going to be x plus 1, or x plus 1, and x plus 2. X plus 1, x plus 2. And then 2x, plus 1, and 2x plus 2. So you could find this complete set of coset representatives just using the division algorithm. And so really then, the elements of this quotient right here really are 0 plus the ideal generated by x squared plus 1, 1 plus the ideal generated by x squared plus 1, and so on. I'm just writing down the coset representatives. Okay, so now, if I look at the polynomial, so now I need to change, now I'm using x, it was a variable, but now it's really an element of the field. So I need to change the variable of my polynomial. So let's use t. So t squared plus 1 will factor as, oh, in fact, it makes it easier to see if you write this as t squared minus 2. And this is equal to, sorry, my eyes are just, I can't see now. T squared plus 2x. This is just the process 2x squared. This is the process that I went through to figure out how to factor this. It's equal to t squared minus 3x plus 2x squared, which is equal to, and now we can see the factorization, t minus x times t minus 2x. So this is happening in f bracket t. All right, so now we're using the variable t because we've got coefficients that live, these are now the coefficients in our coefficient field. Okay, so what does this tell us now? It tells us that our polynomial t squared plus 1 factors completely in f bracket t. And so then the question is, so it definitely splits over f bracket t. Or I guess I should say splits over f. And so then the question is there any smaller subfield of f over which t squared plus 1 splits? And so the answer is no. So since the only subfield of f is, well, I'll say isomorphic to, well, it's really, let me say it this way, the only subfield is 0, 1, and 2. And so you need to check this, that there's no other subfield. But it turns out the only subfield of f is this one right here, 0, 1, and 2. And t squared plus 1 does not split over this subfield. So what does that tell us then? The smallest extension of Z3, right? You can view this as Z3 sitting inside. So the smallest extension of Z3 over which this polynomial splits is f bracket t itself. Right? So conclusion is that f is the splitting field for, well, I don't know. Now that I've changed variables, I guess I should say t squared plus 1 over Z3. So this is an example of what I mean when I say you can get at the splitting field using Kroneker's theorem, right? If you've got an irreducible polynomial, you can root by root. In this case, this extension contained both of the roots of the polynomial. All right, so root by root, you can extend, and eventually you'll build up and find a place that contains all the roots. Okay, so that's the end of this chapter. So we're going to start a new chapter. Sorry, I'm going to close my window just because I got blinded, and now I can't see clearly. Hopefully you can see okay now. All right, so next chapter, this is chapter 3. Normal extensions. Let me see how much time we've used so far. 13 minutes. Okay. So we'll start with the definition. And extension L over K is normal if two things are true. First, it needs to be algebraic. So first thing, L over K is algebraic. And the second condition, for every irreducible, say f in k bracket x, if f has a root in L, then f splits over L. So normal extension, first it needs to be algebraic, and then what it says is, if a polynomial starts to split over L, then it splits completely over L, right? And so such a case, there's such an example, is a normal extension. Let me give you an example of an extension that's not normal. So for example, Q adjoin cube root of 2 over Q is not normal. And here's the reason. If you look at the polynomial x cubed minus 2, this is irreducible over Q. And the cube root of 2 is definitely an element of the Q adjoin cube root of 2, but this polynomial x cubed minus 2 does not split over Q adjoin cube root of 2. Yeah. Right. This field contains one of the roots, but it doesn't contain all of the roots of this polynomial right here. It's missing the complex roots. So here's another example, and we won't be able to actually verify this yet, but it turns out that the extension Q adjoin root 2, I mean, I guess it's easy to check, but we'll get a theorem. So Q adjoin root 2 over Q is normal. It's obviously algebraic, and I just want to say we'll see this later. So we will show this later. Okay, so our next definition, kind of a generalization of the definition of splitting field that we had before. So let's let S be a subset of the polynomial ring K bracket X. So an extension L of K is a splitting field for S over K. Splitting field for S over K if well, let's say it precisely here, but here's the idea. What we want it to do is basically be the splitting field for every polynomial in that minimal sense. An extension is a splitting field for S over K if, first of all, where to go? Right. So if every element of capital S splits over L, and then the second condition, we want a minimality condition. So if we have this situation where we have a field in between K and L, and each polynomial in S splits over M, then M equals L. All right, so there's our minimality condition right there. Okay, so now here's the theorem, and this theorem, there's some hard work involved in proving this theorem. Or at least it's fairly intricate. And so what this is going to do is it's going to totally characterize normal extensions in terms of splitting fields for sets. And by the way, I mean, what we've essentially done in the past, we defined splitting field for a single polynomial, right? And so we defined splitting field in the case that this set S consists of a single element. And now we've just generalized this, we're allowing this set, and this set doesn't necessarily have to be finite, right? It could be an infinite set. An extension L over K is normal if and only if there exists some subset S of K bracket X such that L is the splitting field and I guess technically I should say a splitting field, right? We haven't proved a uniqueness theorem. So it is a splitting field for S over K. Okay, so now let's get to the proof, and this proof definitely is a bit intricate. So in the forward direction, we assume that we have a normal extension, which means it's algebraic, and every polynomial that has a root in L splits over L. So since L over K is algebraic, okay, so what does that mean then? It means that every element of L is algebraic over L. God, I said that backwards. Every element of L is algebraic over K. So that means then that every element of L, for every element, there's a polynomial that has that element as a root. And so what I'm trying to say is that every element in L has a minimal polynomial living in K bracket X. And so that's the set S that we're going to concoct. So since L over K is algebraic, we consider the set capital S equal to, so this is the set of all M sub alpha, where alpha runs through every element of L. Now, what do we know? Okay, so every M sub alpha has alpha as a root. Alpha lives in L because, or by normality, we know that M sub alpha splits over L for every single minimal polynomial, for every alpha. So by normality of L over K, each M sub alpha splits over L. So now the question is it actually the splitting field, right? Is it the smallest? So let's suppose that there's some intermediate field. So suppose we have K, let's call it M. So suppose we have M sitting in between K and L, and that each minimal polynomial, so let's put in that each M sub alpha in S splits over M. So our job then is to show that M is equal to L. And so now what would this splitting look like? Well, it's going to look like, so M sub alpha, if it's going to split, well, we know that alpha is a root, so it's going to have an x minus alpha. And then it's going to be something like x minus beta 1 times dot, 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 x minus beta sub n, I guess. Where alpha and all the beta sub i's are in M. But since each alpha is in L, we conclude that L is contained in M, right? What are we saying? All the alphas live in M. We already know that all the alphas live in L, so that gives us this containment right here. Right, so therefore, L is a splitting field for S over K. That was the easy direction. It's Friday at 2:30 right now, and I know I have office hours at 3, so I'm going to try to, I'm feeling slightly rushed here, but I think I can finish this in a half an hour. Let's say I'm going to finish this baby in a half an hour. So in the reverse direction, so now what we're going to do is let's find our S. So let's say let S subset K bracket X be such that L is a splitting field for S over K. And then our job is to show that the extension L over K is normal. So we'll do that in 2 steps, right? Because there's 2 parts to the definition of normality. We first show that it's algebraic. So we first show that L over K is algebraic. Now, okay, so I'm going to define this set. So let's call it capital A, and it's going to be the set of all alpha in L such that f of alpha equals 0 for some f in capital S. So what do? We run through all the elements of capital L, and we say, are you a root of some of at least one of the polynomials in S? If the answer is yes, put it in this set capital A. If the answer is no, then leave it out. Okay, so A is the set of all elements of L that are roots of some polynomial. So let me just say that. So we'll say so. Capital A is the set of all elements of capital L that are roots of set of all elements that are roots of polynomials in capital S. Now, Of course, each element of capital A is algebraic over K. So clearly, I mean, by construction, right? So clearly, each element of A is algebraic over K. As we said it is. We said it's a root of a polynomial. Now, since both K and A are contained in L, we have that K adjoint A is contained in L. And so here's what I would like to do. If I could show that L is actually equal to K adjoint A, then we have our theorem from I don't remember what theorem it is. It's the corollary 1.8, right? If you adjoin a bunch of algebraic elements to K, you get an algebraic extension. And so if we could show that L is equal to K adjoint A, then we'd be able to conclude that L is that L over K is algebraic. So on the other hand, so I need to get the reverse containment now. So on the other hand, every element of S splits over K joint A. Why is that? Well, because we put all the roots in there. All right, so all the roots of every polynomial in S lives in this field, so it definitely splits in K bracket or K adjoint A bracket X. And now, since L is the smallest subfield over which everybody in S splits, since L is the smallest subfield over which all polynomials in L split, right? We could not have proper containment here, otherwise we'd have K adjoint alpha being strictly smaller, right? And so that forces us to conclude that L is equal to K adjoint A. We conclude that L is equal to K adjoint A. And now we started with K, we adjoined a collection of algebraic elements. It's corollary 1.8. So by corollary 1.8, L over K is algebraic. So there's the first step. And now we need to show that every time we have an irreducible polynomial that has a root in L, then it splits completely over L. So let's take an irreducible polynomial. So let's let f in K bracket X be irreducible over K. And suppose that f of alpha equals 0 for some alpha in capital L. So we're setting the stage. We've got an irreducible polynomial that has one root, and we need to show that f splits over L. Now, we're going to simplify things. First of all, so f is an irreducible polynomial, which means that it is a constant multiple of the minimal polynomial. And so we're going to replace f with its minimal polynomial. If we can show that the minimal polynomial splits over L, then because it's just a constant multiple, f will also split. So since since F is equal to C times M sub alpha for some C in K, it suffices to show that M sub alpha splits over L. So that's our goal. Now, since alpha is in L, which equals K adjoin capital A, there exists, let's call them alpha 1 up through alpha n, in A, do I need them in A? Yeah, an A is fine. Such that A is an element of K adjoin alpha 1 up through alpha n. So what's happening here? Well, we know that K adjoin, every element of K adjoin A can be produced using a finite number of operations involving elements of K and A, which means that all we need is a finite number of alphas, elements of capital A, to produce this one particular alpha. Okay, so now for each I between 1 and n, let, I'm going to call it F sub I in capital S be such that F sub I of alpha I F sub I of alpha I equals 0. And now, what I'm going to do, I want to create a new polynomial, so let's define, I'm going to call this G. So define G equal to F1 times F2 dot 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 F sub n. So, okay, so what's happening here? We take this finite collection of alphas that contains our original alpha. For each one of those, find an element of capital S for which that polynomial has alpha I as a root. And then we multiply all those polynomials together. That gives us this new polynomial called G. And then, so let's let capital R denote the roots, or the set of roots, of capital G. So what do we have? We have all the roots of F1 combined with the roots of F2 and so on, all lumped into one set called capital R. Now, a few observations. The first one, so we know that K adjoint R is contained in K adjoint A, which is contained in L. Second is that K adjoint R is the splitting field for G over K. The third is that alpha is an element of K adjoint R. And why is that? Because each of the alpha i's are elements of R. So we'll say because each alpha I is an element of R. Okay, so now suppose, remember our goal is to keep an eye on what we're trying to do. We're trying to show that m sub alpha splits over L. So suppose that we have beta not equal to alpha is a root of m sub alpha. What do we need then? Well, if we want m sub alpha to split over L, then we need L to contain all the roots. So my goal then is to show that beta lives in capital L. Now the way we're going to do that is we're going to show, the way we'll do that is we'll actually show that beta lives in K adjoint R. And that will then allow us to conclude that it lives in capital L. So, so our goal is to show that beta is an element of K adjoint R, which we know is contained in L, and that will finish it off. So, so note that the minimal polynomial of alpha is equal to the minimal polynomial beta. And so, if I look at the degree of the extension K adjoint alpha over K, right, that's equal to the degree of the minimal polynomial of alpha, which is then going to be equal to the degree of K adjoint beta over K. So now, I'm going to put, I need a little room now. No, I'm going to have to put it up here. I don't want to squeeze it over there. So if you remember, this was back from the proof of 2.5. Yeah. So recall from the proof of 2.5, we had this isomorphism. Remember, so we have K bracket X mod ideal generated by M alpha. We had a K prime bracket X mod ideal generated by M beta. This was the mapping I tilde. That was an isomorphism. And then this went to K adjoint alpha via E sub alpha tilde. This one went to K prime bracket beta by E sub beta tilde. All right, so remember we had then this composition which we called J, right? And that was an isomorphism. Now, what we initially required, right, was an isomorphism from K to K prime. Now, it was really a monomorphism from K into some L, but then we looked at the image of that and called that K prime. So, so in the case that we actually just start off with K equal to K prime, and it would have been I equal to the identity map, then, well, then what that does is it basically takes this portion out of the picture, right? Because I is just the identity map. So we get an isomorphism. Then we have an isomorphism, which we'll still call J, and it'll go from, let's just say, well, okay, it's fine. K adjoint alpha to K adjoint beta. Remember, K is equal to K prime. Defined by J equals E beta of E, or tilde, sorry, E beta tilde of E alpha tilde inverse. And what is it? It's an extension of the identity that takes alpha to beta. So such that J restricted to K equals the identity, and J of alpha equals beta. Okay, so let me just draw a little diagram that'll help us sort of keep our head straight. So that's the identity map. We've got K adjoint alpha, K adjoint beta. We have inclusions in this direction. And then we've got J right here. Now, I want to now consider, we're going to sort of add another rung to this ladder, so K adjoint R beta. These are inclusions once again. Now, since K adjoint R is the splitting field for G over K, and K adjoin R comma beta is the splitting field for J of G. Oh, but let's think now, J of G. So the coefficients of G live in K, and J restricted to K is the identity, so it doesn't do anything to the coefficients of G, which means J of G is actually just equal to G. There exists an isomorphism call it sigma from K adjoin R to K adjoin R together with beta, such that sigma restricted to K adjoin alpha is equal to J. This is corollary 2.8, right, which told us how to extend over splitting fields. So now we have a map like that, sigma from here to here. Okay, so the last step, we're almost there. So it follows that the degree of K adjoint R over K is equal to the degree of K adjoint R beta over K. Sorry. I just this is what I'm trying to prove. I just lied here. Sorry. Well, I didn't lie, but I need to actually prove this. Okay, this is K adjoint R over K alpha is equal to, sorry, K adjoint R together with beta over K adjoint beta. There we go. So now I need to apply the Tower law. So by Tower law, the degree of K adjoint R over K is equal to the degree of K adjoint R over K adjoint alpha, K adjoint alpha over K, which is equal to K adjoint R and beta over K adjoint beta, because these are equal. K adjoint beta over K, we know that these are equal. And then we can put this back together. This is K adjoint R beta over K. So now what do we have? We have K adjoint R, we know is a subspace of K adjoint R and beta. These have the same degree, which means they have the same dimension. And so since this is a subspace of this with same dimension, they have to be equal. So since K adjoint R is a subspace of K adjoint R and beta, we conclude that K adjoint R equals K adjoint R beta. In particular, then, beta has to live in K adjoint R. So we can finish this off with one sentence or so. So therefore, beta is an element of K adjoint R, which is contained in L, and so all the roots of M sub alpha live in L, so M sub alpha splits over L. Okay. Notice I said something about that theorem 2.5 being important, right? We've seen how it comes into play. It allows us to extend, and we needed that extension. We needed that isomorphism to make that conclusion right there. Once we had this conclusion, then we could just run the Tower law to get equality or containment, which gave us we already had containment, which gave us the equality here, right? And that was what we needed. All right, good place to stop because my office hour is going to start in a couple of minutes, so we'll see you then, or see you next time.